Optical density redirects here. Optical density can also refer to index of refraction. In chemistry, absorbance or decadic absorbance is the common logarithm of the ratio of incident onto transmitted radiant power through a material, and spectral absorbance or spectral decadic absorbance is the common logarithm of the ratio of incident onto transmitted spectral radiant power through a material. Absorbance is dimensionless, and in particular is not a length, though it is a monotonically increasing function of path length, and approaches zero as the path length approaches zero. The use of the term optical density for absorbance is discouraged. In physics, a closely related quantity called optical depth is used instead of absorbance, the natural logarithm of the ratio of incident onto transmitted radiant power through a material. The optical depth equals the absorbance times lane. The term absorption refers to the physical process of absorbing light, while absorbance does not always measure absorption. It measures attenuation. Attenuation can be caused by absorption, but also reflection, scattering, and other physical processes. Mathematical definitions. Absorbance of a material, denoted A, is given by where phi A is the radiant flux transmitted by that material, phi A is the radiant flux received by that material, T is the transmittance of that material. Absorbance is related to optical depth by where tau is the optical depth. Spectral absorbance in frequency and spectral absorbance in wavelength of a material, denoted A nu and A lambda respectively, are given by where phi E, nu T is the spectral radiant flux in frequency transmitted by that material, phi E, nu I is the spectral radiant flux in frequency received by that material, T nu is the spectral transmittance in frequency of that material, phi E, lambda T is the spectral radiant flux in wavelength transmitted by that material, phi E, lambda I is the spectral radiant flux in wavelength received by that material, T lambda is the spectral transmittance in wavelength of that material. Spectral absorbance is related to spectral optical depth by where tau nu is the spectral optical depth in frequency, tau lambda is the spectral optical depth in wavelength. Although absorbance is properly unitless, it is sometimes reported in arbitrary units, or O. Many people, including scientific researchers, wrongly state the results from absorbance measurement experiments in terms of these are made-up units. Relationship with attenuation. Attenuance absorbance is a number that measures the attenuation of the transmitted radiant power in a material. Attenuation can be caused by the physical process of absorption, but also reflection, scattering, and other physical processes. Absorbance of a material is approximately equal to its attenuance when both the absorbance is much less than 1 and the emittance of that material is much less than the absorbance, where phi A is the radiant power transmitted by that material, phi E is the radiant power attenuated by that material, phi A is the radiant power received by that material, phi E is the radiant power emitted by that material. T equals phi A is the transmittance of that material. At equals phi A is the attenuance of that material. E equals phi A is the emittance of that material. And according to Beer-Lambert law, so, attenuation coefficient absorbance of a material is also related to its decadic attenuation coefficient by where L is the thickness of that material, through which the light travels. A is the decadic attenuation coefficient of that material at Z, and if A is uniform along the path, the attenuation is said to be a linear attenuation and the relation becomes. Sometimes the relation is given using the molar attenuation coefficient of the material, that is its attenuation coefficient divided by its molar concentration, where epsilon is the molar attenuation coefficient of that material, C is the molar concentration of that material at Z, and if C is uniform along the path, the relation becomes The use of the term molar absorptivity for molar attenuation coefficient is discouraged. Measurements, logarithmic versus directly proportional measurements. The amount of light transmitted through a material diminishes exponentially as it travels through the material. According to Beer-Lambert law, since the absorbance of a sample is measured as a logarithm, it is directly proportional to the thickness of the sample and to the concentration of the absorbing material in the sample. Some other measures related to absorption, such as transmittance, are measured as a simple ratio, so they vary exponentially with the thickness and concentration of the material. Instrument measurement range. Any real measuring instrument has a limited range over which it can accurately measure absorbance. An instrument must be calibrated and checked against known standards if the readings are to be trusted. Many instruments will become nonlinear starting at approximately 2 astronomical units. It is also difficult to accurately measure very small absorbance values with commercially available instruments for chemical analysis. In such cases, laser-based absorption techniques can be used, since they have demonstrated detection limits that supersede those obtained by conventional non-laser-based instruments by many orders of magnitude. The theoretical best accuracy for most commercially available non-laser-based instruments is in the range near 1 astronomical unit. The path length or concentration should then, when possible, be adjusted to achieve readings near this range. Method of measurement. Typically, absorbance of a dissolved substance is measured using absorption spectroscopy. This involves shining a light through a solution and recording how much light and what wavelengths were transmitted onto a detector. Using this information, the wavelengths that were absorbed can be determined. First, measurements on the blank are taken using just the solvent for reference purposes. This is so that the absorbance of the solvent is known, and then any change in absorbance when measuring the whole solution is made by just the solute of interest. Then, measurements of the solution are taken. The transmitted spectral radiant flux that makes it through the solution sample is measured and compared to the incident spectral radiant flux. As stated above, the spectral absorbance at a given wavelength is the absorbance spectrum is plotted on a graph of absorbance versus wavelength. A UV-vis spectrophotometer will do all this automatically. To use this machine, solutions are placed in a small cuvette and inserted into the holder. The machine is controlled through a computer and, once you blank, it will automatically display the absorbance plotted against wavelength. Getting the absorbance spectrum of a solution is useful for determining the concentration of that solution using the Beer-Lambert law and is used in HPLC. Shade number. Some filters, notably welding glass, are rated by shade number, which is 7/3 times the absorbance plus 1, or where SN is the shade number. So, if the filter has 0.1% transmittance, the shade number would be 8.